Professor Lucas Goering. He's from Nottingham Trent University and also from MPI Göttingen.
Thank you, Vikas. So I'd like to talk today about something that might remind us a bit of Daniel's talk yesterday. This is an artificial, tunable, basically what I think of it as model sandstone. These are sort of a new kind of material that we've been investigating for the last year or so. This is the first time that I've had the chance to talk at a scientific audience about this. So some of the slides might be a bit new here. So this is work which is largely the postdoc work of Arnaud Hemmerle, who is now in Marseille, doing a second postdoc. Actually, a lot of the fracture stuff, which would be most relevant to this audience, was done by a very talented master's student of mine, Alexander. And the granular support comes from a granular scientist, Matthias Schroeder. So the idea we're thinking of is basically imagine a sand castle. You have grains of sand held together with water. If you freeze the water, you have a material which is cohesive and rigid. And this is the kind of material that we'll be exploring. So first, I'll give you the recipe for this. How do we make it? What is our inspiration? What do we want to do with it? And then I'll work you through the physics of it. How does it deform? How does it yield? How does it break? And then in the last part, I'll start exploring, this part is still in progress, how we go from the microscale physics of contacts between individual beads to the macroscopic properties. So cohesive granular materials can be thought of in a broad sense as stuff which is granular, which is held together by some forces. We've seen this in some colloids, for example, over the last few days. We've seen it in Daniel's talk with his sintered plastics, PDMS. But some natural examples, for example, snow, soils, sandstone is what we're basically trying as our fundamental point. Colloids and composites. This is a crack going through a colloidal material like paint. From the previous talk, there was talk about yielding. You can see defect lines, etc., bridging microstructural damage from the crack going through the paint. That's something I studied a number of years ago. This is sort of an extension of that. The kinds of problems that might be appropriate for this, the things that we want to study here ultimately, involve fracture and failure in cohesive materials. So all the examples here, there are concerns about failure. What happens when these fail? And however, in order to study those processes, using natural materials is challenging to get the reliability, repeatability, and in some cases, the material properties might not be just what you want, but there's no real ability to change them. So what we want is something tunable, reliable, repeatable, easily produced, cheap, etc. For example, here's a case where we're working with a fellow in Oxford, Chris McMinn. He's done a lot of injection type experiments, and here we will be looking at fluid injection for hydraulic fracture. When will pushing water through a cohesive material like a sandstone be able to provide enough pressure to break that system? Additionally, on the biophysical side, I'm very interested in the mechanics of endoliths, extremophiles, and things which inhabit rock, lithophiles. This is largely from a sort of extremophile point of view. These are very interesting creatures. They live in very harsh environments. Their life cycles are very, very strange. For example, the one pictured there is from Antarctica. It lives a centimeter below the surface of the sandstone, where it is protected from the environment, but there's still enough light to photosynthesize. Its life cycle involves growing long enough that it breaks off the rock. The bits flick around in the wind and recolonize a new surface. The important thing from cultural heritage, and restoration of cultural heritage involves the damage that microbes can do to sculptures, for example. When can biology break rock? Under what conditions? And now from a basic fundamental sort of physical perspective, the questions involve what sets the mechanical properties of this class of material? Well, basically we have grains, we have solid bits, and we have contacts between them. And then there's typically some pore space between that as well, which allows for fluid to flow. Most of the cases that I've talked about can have multi-phase flow through them. So they're porous materials. And so in the case of snow, you basically have grains of snow which connect together, jam, can be compressed into fern or other materials, ice even, and have mechanics like that. Sandstone is grains of sand connected by interstitial material or void, held together like that. These tend to be weak and break. For soils or sintered materials, you might have connections between them of some other kind of material, for even for example, water, moisture, for example, which will help a sandcastle stay up. All of these are very complicated materials. And so the problem involves many different kinds of concerns. We have different kinds of interactions, we have different kinds of contacts. Hard things contacting hard things have a nonlinear contact force, which may be different from the soft kind of cemented contacts. There are many body interactions. For example, if you try to deform this pair of particles, you'll end up also deforming the particles around it. You can have multiple phases. You can have cemented contacts, cemented pore spaces. You can have weird shapes which just jam by their shapes alone. For example, think about the snowflakes. And you can have size, polydispersity, et cetera, et cetera. All of this makes studying such materials very challenging. So what we're going to focus on is trying to understand the simplest possible situations which we can to build these materials and to use these materials as models for more complicated situations. In that case, we're going to focus on cemented contacts and the basic effects of this many body interactions, which were already known from classical granular physics. And to do this, we'll look at material which consists of sand and a bit of plastic. The plastic is added as a liquid form. It moves it's perfectly wetting the glass beads, which is basically sand, in an idealized physicist's form. Glass beads, it wets the glass beads, and it forms contacts between them, capillary rings holding the particles together. So basically, as I said, you can think of a sandcastle. The sand has a few % of water in it. It doesn't really matter how much water is there. It still has comparable elastic properties. And that's a nice, robust feature of wet sand. That's why you can build a sandcastle. And if you take that and you freeze the water in place, you preserve the geometry, you preserve the structure. You have these glass beads or sand held together by pendular or capillary rings containing now solid phase. So basically, we've got glass beads held together by plastic bridges. We can change the stiffness of the bridges, we can change the volume of the bridges, we can change the size of the particles. Using this, we can have a tunable elasticity, we can have a tunable fracture toughness, and we can have tunable other properties like permeability or porosity. And so it's also a inert scaffold if you want to look at chemical or biological processes. The basic idea is it's a very simple recipe. Take glass beads, you clean them, you dry them. They can be pretty much any size you want in terms of getting them from the manufacturer. You then take PDMS, which is a curable polymer. You mix it together with a base, which is basically the polymer chains, and another liquid which cross-links those chains. And by varying that ratio, you can then vary the stiffness of the product. You mix them together. You then mix that and you pour that into the beads, you mix it in the mortar and pestle, and you have something which behaves a little bit like cookie dough. And you can mold it into the shape you want, and then put it in the oven, bake it overnight, and it comes out as a rigid body. You can make any structures you want. We'll be looking at a classic compact specimen fracture test later. Cylinders, you can make any shape you desire. So we're now talking about, as I said, a sort of novel class of material. We're talking about granular matter, but where we have cohesion between the grains. And so we're trying to build from the physics of granular matter into this new field. Wet granular matter has been studied for a while. This is a limit which is actually also appropriate for many colloids. This is where you have an adhesive force, where if you break it, they will re-stick to each other. This is subtly different in that if you break these bonds, they will not typically reform. So if you look at it under microscopic sense, if you look close up, you'll see glass beads. You'll see what look like capillary bridges of water or liquid between them, but these will be now rigid and solid in place. It's tunable because we can change the stiffness, we can change the material properties. And we can change the stiffness of these bridges. We can make them bigger, we can make them smaller by just adding more or less polymer. We can change the size of the beads, etc. So now the questions we're interested in are how do the macroscopic properties of a block of material like this depend on the microstructure? And basically, how can you understand that? So in terms of that, what sets the stiffness of the material? How does it deform? How does it fail? Can we learn anything general about failure, yielding, or plasticity, or fracture of materials in general from looking at this model material? And what sets its strength? So in order to look at that, we basically must characterize the material properties and look at them under extreme situations. So we have a couple kind of test environments. We have a uniaxial compression load cell. We put the block of material in there. We compress it. We squish it. And we look at the response. This part was published about 3 months ago in Scientific Reports. So you compress it. You put it in. You start squishing it. And you get, as was introduced in the last lecture, a stress-strain curve. The stress is the amount of, the stress is basically the force that you're applying on the surface divided by the area of that surface. It's a cylinder that's easily well defined. The strain is the difference in height between what it is at one point and when you start it. Now, immediately what we find is there's no Hertzian contacts. There's a nice broad linear region here. And the elasticity is much softer than the beads. The beads are glass. They have a modulus of about 60 gigapascals. We also see a few features. Because the surface is irregular here, the beads are sort of packed into a cylinder, but the surface has irregularities on it. The contact region takes about 1/2 bead diameter, or 1 bead radius, in order to make contact. And so you see a little nonlinear region there. That's simply because you're making contact. One bead might be poking up a little bit more. You touch that one first before you make good contact with the surface. After that, there's a broad, well-defined linear response where you have a Young's modulus, basically by reading off the stress-to-strain curve. After that point, you get yielding. We're defining yielding by the initial deviation from the linear region. It doesn't really matter which definitions you use. You can use the top. But as long as you use a consistent definition, it is reasonable here. So, yes, you were first. What is the flat region? Which after yielding here?
No. This for small strains.
This?
Yeah.
As I said, that's when you're making contact. So this is a series of bumps on the surface because the beads are irregular. You hit the top one, you hit the next one, and by the time you reach 1 bead radius, you've hit on average, you've made good physical contact with the surface. And so that it really depends where you define strain equals 0. We define strain equals 0 as the first measurable force. So so that we're not imposing any definition which basically you could also backtrack from here and say that's strain equals 0, but we felt that was a bit too arbitrary. So it's the first place where a measurable force is measured. There was a question there. It's close to close packing. It's about 60%. So it's below random close packing, but it's about 60%. This is actually very similar to wet granular matter, where the packing is a little bit lower than you get if you have a dry granular packing. And so the physics is very similar in that regards to wet granular material. At the back as well.
So, in this elasticity, so if you just compress the material and release it, will it come back to the original shape? And
yes, there is a small amount of hysteresis, which depends on how quickly you do it. but we are in the limit where if you measure a back response, it will be the same slope. There may be a slight offset to that, depending on how fast you do it. And once you go into the yielding, of course, there'll be an irrecoverable strain. But yeah, we can push and come back. We've done those tests quite often. Okay? Satisfied? Very good. So where were we? Right. So as I said, the one key point here is, as I said, the Young's modulus of the beads is measured in gigapascals. The stresses here we're talking about are kilopascals. And the elastic modulus of these materials are kilo to megapascals. So we are dominated largely by the softer phase, despite the polymer occupying about 1 to 3% typically of the volume fraction here. It is dominating the physical response. So what we can do is then tailor the polymer. If we just make a disk of pure PDMS, which is easy to do, we can then look at its elastic response. We can put that in our compression cell. It also serves as a validation check if our compression cell is making the correct measurements. So we can look at the elastic response of the polymer. The polymer, depending how much cross-linker you have, has a Young's modulus varying between a kilopascal and a megapascal. And so the stoichiometric ratio is 10 to 1. So if you use less cross-linker than that, you have a softer material. The very softest ones are actually tacky to the touch, so they're a little viscous as well. So those ones sometimes have peculiar characteristics. Our data is the black, the rest are other measurements of this. PDMS is a well-known material, it's used in microfluidics, so it's a well-studied material. So our data is consistent with that. If you then use that as your control parameter, so we're taking the elasticity of the polymer, we're then using as a control parameter. We're keeping everything else constant, so we have beads which are 210 microns, and we add 2.3% of polymer. Error bars are a result of 3 replicates. Then what we see is this is the line we would get if the response of the material, the composite, is the same as the polymer. It's about a factor of 10 larger. As I said, the softest materials often deviate because the polymer is probably still slightly fluid. So we find the composite material has a stiffness which is controlled by the stiffness of the polymer phase and is about an order of magnitude higher. We can then vary the polymer content. In polymer content, there's an important distinction. When you start adding water, you make these capillary, or liquids, right? You make these capillary rings larger. Eventually, the rings will touch each other, and you'll have a transition which is known in the community as the pendular. These are often called pendular rings because they're pendant around the contact, to funicular. And I've never really understood why they use the word funicular, but hey, that's what it is. Where the pendant rings touch each other. And when you start adding fluid to this, it goes into the throats between the particles. So the pendant rings stay approximately the same size, and as you add more and more fluid, you're adding it to a place which is not actually important to the elastic response. So there are 2 fundamentally different regimes, and we find the transition between those in our material about 3%, which is consistent again with wet granular materials. We can measure that directly. We can look at the cross-sectional area of the bridges under different cases. So we make a material, we look under the microscope, and there's a large variation in the size of the cross-sectional area. The black dots are the averages, but the first places where we see trimers, where the liquid is filling into the space between the beads, also corresponds to A star is, you can calculate based on a tetrahedral arrangement of beads, or a close packing arrangement of beads. You can calculate geometrically the amount of fluid you can add in before they start contacting each other. And that's this A star. So we find that the pendular to funicular transition occurs basically exactly where the first bridges become large enough to touch each other. So if we then look at the elastic response, this is the pendular to funicular transition here. And so you can see there's a distinct change. Below this, we have an elastic variation. We have a linear variation of elasticity as a function of the amount of polymer content. And above that, there's again a weak dependence on that. If we look at this in terms of area, we basically find that the elastic response varies with the area of the bridges. So if you have two beads connected with a small area and two beads connected with a larger area, the elastic response, if you try to stretch them or compress them, will depend on the area of the contacts, which physically, intuitively makes sense. All the force is compressed onto that, between these two beads, and if it's a polymer material, it's compressible, it's squishable, and so that sets the elastic response. Last thing we can do is change the particle size. Now, mechanically, if you think about this, changing the particle size but keeping everything else constant, if you have perfectly wetting material, should just basically zoom in or zoom out on the material. And because linear elasticity has no fundamental length scales in it, other than those imposed by the geometry, this actually should produce no change to the elastic response. There is a subtle change. This is a logarithmic scale, this is a linear scale, so there's a weak change. And we'll come back to that later. What this weak change implies is there is actually an additional length scale in the problem. And from this observation, we suggest that there's a small gap between the particles, which is actually strongly influencing the elastic response, 1 or 2 microns. Okay, so summary of our stiffness observations. We've been looking at these granular materials, which are cohesive, held together with plastic bridges. We find that the elastic response of the medium, the composite material, is controlled by the minority phase, the polymer, which is in the bridges, even though that's about of order 2 or 3% volume fraction. The elastic response is about an order of magnitude higher than that of the polymer phase and can be controlled by changing the polymer content or the polymer stiffness, and weakly if you want to change the particle size. So if you could use all these together, you can find a factor of a few hundred in terms of the tunability of the elastic response. This is only working with PDMS, so you could presumably do the same experiment with stiffer polymers if you wanted to make a harder material as well. So, moving on to the next question. How does it fail? This is more relevant to the group here. So I showed you a few stress-strain curves. We saw plastic deformation at large strains. And this is just a few of them. This is with different polymer contents, stiffer material, softer material. They all have basically the same shape. At large strains, they fail. Strain being large in this case is actually about order 10%, which is comparable to the kinds of strains that were seen in the modeling of the polymer, the colloids, that was just shown. And if you look at all the different experiments we did, as I said, we could vary the polymer content, we could vary the polymer stiffness, and vary the particle size, a range of several hundred in terms of the elastic response. If you look at the yield strain, which we define as the onset of deviation from the linear elastic response, we find the yield strain, there's some scatter, but there's no obvious dependence on anything. Here we just plotted it as a function of the ratio of the elastic response to the polymer elastic response. As I said, it's typically about 10 because we had to plot against something, but there's no obvious dependence on anything that you can try there. Basically we always get a yield strain, it breaks down to the finite strain of about 8% is the average. So if we want to look more closely at this, we can do X-ray tomography. So we then take our load cell. We actually had to build a new one because it didn't fit. We make a load cell which goes into an X-ray tomograph, and we then compress it while taking 3-dimensional X-ray images of the system. So we have an X-ray source, it smashes through, and this rotates and then moves up and down, and you get, in a few hours, a image of that. You then start compressing it to a new state. You measure the stress strain. You then stop, image, and repeat. This is a very slow process. It takes about a day or two, i.e. over the weekend, in order to run an experiment. So typically we would set it up on Friday, open it on Monday, and hope something happened. The kind of data we get, however, is extraordinary. We have very high quality imaging of the particles. We can even see the bridges between them. And we have XYZ coordinates as we compress. So if you label them with color by bead number, you can see the bead statistics. You can go to the granular community. This is not something I'm an expert on, so bear that in mind if you have questions. What we can ask, yes?
Yeah. So you get these particle positions by scanning.
Yes.
So what is the speed of scanning compared to the natural time scale of the particle?
These are macroscopic. These are a few hundred microns, so there's no Brownian motion. If you're thinking comparing to colloids, a 200 micron particle has no Brownian motion. So that's effectively irrelevant. So there is a time scale for the scan. It's a few hours, but we tried a few variations on that. We can see everything clearly. There's no blurring, and we can see clean positions of everything. And it would blur if it moved by more than a few microns. The voxel resolution here is about a micron or two. So in order to do this carefully, we also need monodispersed materials and everything. So these are very controlled experiments. As I said, if you're a granular physicist, this will mean more to you than it does to me, but we can do all the kinds of statistics, characterizations that you would if you had if you were working with a granulate. You can look at the pair correlation functions, G of R. You can look at the peaks here and correlate them with the nearest neighbor, second nearest neighbor interactions. And again, the result of that is the structure of this is very similar at its core to a wet granulate. Said the difference is there, if you move something, for example, if you take two spheres which are touching with water and you rotate them, the water will just follow it around. In this situation, if you do that, you're introducing a deformation which is elastic. So there's differences on that sense. But structurally, we're very similar to a wet granular material. So now if we start yielding again, if we follow compression, if we then make 5 scans here, 1 before contact, or 0 before contact, 1 where we first see the first forces, 2 at the beginning of the linear regime, 3 at the end of the linear regime, and 4 into the yielding regime, we can follow the beads and look for local deformations. Again, similar to some things we've seen in previous talks. So you can compare these pairwise, subtract one from the other to look at the deformation field. If we go from between 1 and 2, there's no localization. There's some features near the surface, which again is dealing with how we make contact with the surface, but the deformation field is uniform throughout. Between 2 and 3, it's largely uniform. You're beginning to see that the onset of a strain or a shear across the entire sample, but it has not localized. Between 3 and 4, however, that strain localizes and we see the beginning of a shear failure. There's a slip plane here. This is, again, very similar to the kinds of compressive failure you would expect in most materials. If you take a cylinder of material and you compress it, the direction of maximum shear strain, the first place you'll reach a yielding criterion is at around 45 degrees to the slip plane. There is some discussion about this in granular materials because the introduction of friction into the system can change that direction slightly, but for homogeneous material, it'll be at 45 degrees to the axis of compression. So you can imagine this, basically the sample wants to get smaller. It can't necessarily do that. If it slips along both these directions, the whole sample will have ultimately been compressed. And so that's one sort of intuitive reason why that happens, why that is the physical response. A mixture of shear bands in both directions allows for compression. Additionally, and again, this is similar to what we just saw, If you're compressing this, there's only so far with an affine deformation that you can go before the particles will start slipping past each other. So if you take your knuckles and do this, you strain them, eventually they'll slip into the next local minimum. And so this is actually something which is seen often for particles which are caged in emulsions and colloids. I've done some work on the colloids myself, but it's also well known for emulsions where there's a yield strain to the material rather than the yield stress, which is more characteristic. And that's because you are sampling something where if you just deform the geometry of the cages enough, they'll jump into the next minimum. So this is basically what we're seeing here. It's acting as a yield strain material with a high yield strain. Was there a question? Okay. And the strain then localizes on a slip plane, shear localization or shear banding. And so some of this work we've actually talked quite well with, there's a group in Rennes looking at the shear failure of granular materials where there's a pre-stress to it, so it's confined. And there's some very strong similarities between the physical situations in the two cases. Again, cohesive versus adhesive. There, the forces will reassert themselves if they slip to the next particle. Here, the bridges will not. So, moving on to the next topic, are there any comments or questions about the yielding before we do so? Any rebinding?
Yeah, when you break.
No, we never really see that. Basically, they, as I'll show you later, they tear off each other, and they don't reform. No. So, anything else? You can try stick the things together and they'll just fall apart. There's, I mean, you can do that kind of a test as well. Yes.
Sir, is there any tension compression asymmetry? What if we do tension test on this material?
So the next part will be on the tension. We can actually measure using compact tension tests the elastic response. I'm not showing that today, but we can also measure an elastic. So if we pull on this, we can also measure an elasticity, a Young modulus. It's not as clean in experiment, but we can get an elastic response, and we see no asymmetry between the tension, the Young's modulus under small tension, and the Young's modulus under small compression. So it seems that there's no obvious asymmetry in that direction. Other questions? Yeah.
You wrote that the system is homogeneous, but when you
well, I was talking about this as homogeneous. This is just sort of the cartoon. Our system is not. It's a granular material. It's not homogeneous by any means.
in the preparation, don't you have more of the pendular system, more of the pendular structures at the bottom than at the top, or?
No. We've been careful to avoid that. Basically, you can look at the length scale over which capillary rise in these kind of materials will act. And if basically you can set a limit on how high you can go before gravity will matter. Even in the largest of our beads, that's a few centimeters. And we tested that by actually, so one of our basic tests, there are two tests. One, we basically made one this way and then another one upside down and measured the elastic response, no change. We also made a tall sample, then sliced it into 3 and measured the elastic response. This is again with the largest of our beads. And this is now something which I think is several centimeters high, sliced into the top centimeter, bottom centimeter, middle centimeter, and check that. So in the samples I've shown you, there is no effect of gravity. There's no settling of the polymer to the bottom. I mean, if you look at a sandcastle, you can build a fairly tall sandcastle before you'll get a fundamental difference between the material at the top and the bottom. That's what we're sampling here. So there is a limit, which you can calculate back of the envelope based on the capillary pressure and gravity. The capillary pressure in the pendular rings and gravity. It's a few centimeters for our largest bead size. Of course, if you go beyond that, yes, you'll assume something will happen. But in that sense, it is homogeneous that we've tested. Anything else? Okay, then let's continue. Fracture. So how's it break? And again, this is something which was just been published. It appeared yesterday in the accepted versions of Soft Matter. So this is really fresh off the press. If you look on Soft Matter webpage, it'll be there as of yesterday. And this is again I'd very much like to thank in particular the work of Alexander, who was a master's student. This is his master's project. So we're looking at how it breaks. Here, as I said, we can mold this material into any shape we want, and so we make compact tension test specimens. Here, basically, we have a pre-notch, a pre-crack, and we pull with forces along these holes, and that creates a tension at the tip of the notch, and when that gets large enough, it breaks. And that's the result. You can see there's a crack growing off the surface now. You can monitor as observable the opening of the mouth, and that gives you a proxy for strain, and the stress again is the force applied through here, and that gives you a measurement which can be converted to a stress at the tip. And then you monitor until failure occurs at the tip. Basic fracture mechanics, not necessarily necessary for this audience, but some of the students might still benefit. If you have a crack, the stress lines get deflected around it. There's a stress singularity at the crack tips. This clears out something which geometrically has an area about the size of the crack squared, which then is relatively stress-free. So there's focusing on the crack tips, and there's a stress release. If you turn that into energy argument, as Griffith did, if you have a crack of size A, it costs a surface energy to create that, or an interfacial energy to create that new surface. And the energy released goes as A squared. Basically, it's the energy of that region which is released. You compare those two, and you can basically get a critical conditions for fracture that relates when these two balance each other when you want to make the surface slightly larger. Also done by Irwin, if you have a crack of a certain size, there's a characteristic singularity of the stress there. The intensity of that singularity is something known as the stress intensity factor, and basically Irwin says that any material will have a characteristic resistance to breaking when when the magnitude of that divergence reaches some critical value. This can be consistent with the energy argument if you make a balance between the critical stress intensity factor and the Griffith energy. So one's the square root of the other. And the elastic response, basically the Young's modulus, sometimes it's scaled with a Poisson ratio depending on the subtleties of the loading conditions, is the constant proportionality. So we can view this in either sense. And so what we do then is we can look at varying the bond stiffness. We want to know how the material breaks. So we pull it until it breaks. As I said, we can measure the stiffness. The stiffness is consistent with the measurements in compression. And so if you make a stiffer material, but you have the same geometry, in other words, the same amount of fluid there. In this case, we have a bead size of 210 microns and 2.3% of polymer in there. So basically, we're making the same geometry stiffer and stiffer and stiffer, but keeping everything else about it constant. We can then measure the fracture toughness. What we find there is the blue are the mean measurements of multiple observations. The scatter here, for example. And so if you look at the blue, basically you find that it agrees with a constant fracture energy. So as we're changing the stiffness of the material, the fracture toughness changes, but the fracture energy is consistent at about 10 joules per meter squared. This is well into this type of brittle limits that one might expect. We can change the polymer content again. Remember, this changes the area of the bridges that form. And again, we can look at the fracture toughness. We find the fracture toughness scales with the area. Because the elasticity of the material also scales with the area, this says that the fracture energy, the amount of work it takes to break an area of the surface, an interfacial area, depends with the area of the bonds on that surface. So basically, we're breaking the bonds. If you have bigger bonds, it takes if you have bonds which cover twice as much area, it takes twice as much work to break them. So it scales with, as you might expect, the area of the bonds across the newly created fracture interface. So basically, we find a well-defined fracture energy. It's consistent with a brittle type behavior or close to brittle, and we find that it scales with the area of the broken bonds. We can then, again, as before, look at the microstructure of this with Xray tomography, and we can see those broken bonds here. We can also see intact bridges under the tomography. This is the fracture interface. This is below it into the sample. So we can actually penetrate deep into the material. And then you could identify two different kinds of mechanisms by which this would fail. Adhesive failure, where the bond basically peels off the surface of one of the bridges or one of the beads, or the polymer breaks internally. We know the surface or interfacial energy of glass on PDMS. It's about 7 joules per meter squared. It's been measured, perhaps even by people in this room. And we also know the cohesive energy of PDMS. To tear it is much more expensive, 250 joules per meter squared, which is too high. So we can eliminate that based on physical grounds. We can also eliminate it based on our Xray tomography. You can see all these leftover rings, cups, basically, and you can even see the impression of the previous bead there. So basically, they peel off one of the beads, leaving it behind. We can also look at the statistics. If we look at this fracture surface or fractured interface, we can look at the Xray tomography after failure has occurred. We find that failure occurs by the loss of one bond per particle, or 2 bonds per one bond sticks to this one, and 1 bond might have been here. So it depends on how you count them. 1 bond per particle along the interface, or 1 or 2 bonds per particle along a surface. Depends on how you count surface versus interface. The language is inherently messy. So this particle will retain one extra ring, and there will be a place on average where one has vanished. And it turns out this is just enough to reduce the coordination number of these beads to 6, which is where you have a loss of rigidity. We're not obvious whether this is just a coincidence or whether that this actually is inherent to how these things break. They basically break by failure of bonds until they go from a rigid to a floppy material. Speculation at this point, but an interesting similarity at least.
What are the rings?
The rings are these broken capillary rings. So this would have had another ball sitting right here that is now torn away on.
White.
Oh, these imaging artifacts. Sorry, that's just imaging artifacts. This is a stack of images producing a 3-dimensional structure, and sometimes there's variations in intensity as you go down that stack. Those are imaging artifacts dealing with the way the Xray structure was, or the Xray tomograph was made. Anything else? No. Then, as I said, if we look at a particular, our material was mostly done at a particular volume fraction. If you look at the area covered by the beads, they're about 10% or 12% of the interfacial area. So you expect, if you're only giving the energy to breaking those interfacial beads or bonds, you expect the fracture energy to be 12% of the interfacial energy of the PDMS on glass. It's a little bit higher. It's about 7, or it's about 10 times higher. So the conclusion is it's very nearly brittle, but there's still some plasticity. You can actually identify this. If you look closely at the material, you can find damage up to about 2 particles deep. Yesterday there was some discussion in Daniel's talk about whether this is plastic or there's a process zone around his fracture. Here you can see by X-rays there's a small process zone that extends about 0.5 millimeter or 2 particle diameters. So in summary, for the fracture part, we can tune the fracture toughness by about a factor of 20. The fracture energy we find scales with the amount of material that is breaking. And we can find that we have a fracture occurring by adhesive failure. Basically, the PDMS rips off the surface of one of the particles. And there's an intriguing loss of rigidity at the very fractured tip, which may be associated with how it breaks as well. Last part of the talk will be trying to do a little bit going from micro to macro. So the questions on the fracture part. This would be a good time for them. Yes?
You're saying that the fact that GC is more like gammas and 0.12 gamma is associated with plasticity, but I guess it's defined with the surface
yep.
at a large scale.
Yeah, there's some...
The surface at micro scale, which
yeah.
is rough, can you fit the
Not quite a factor of 10. It seems awkward to fit a full factor of 10. A factor of 2 or 3 might be more realistic. It's a reasonably flat surface. So it's not, you can see, actually I don't have any pictures of that. It's not particularly rough. There was one picture where you could see the crack. So it's not particularly rough on the microscale. But yes, that is obviously something that we're not accounting for because it's too challenging to measure. The tomogram is, yeah, on the tomogram there. Was there another question? Yeah, back there. No, I'll show you some observations where we did microstructural, we basically looked at the constitutive relationship of individual bridges, and that's what's next. And no, there is a large scatter in that. But it's a scatter of a factor of 2 or 3. It's not a scatter of 50. It's a small scatter in some sense, but there is a significant scatter there. Anything else? Okay. Then we'll move on to the microstructure. Okay, all this again. Where are we? Last part. All right. So here, basically, we'll start playing with pairwise interactions between particles, trying to understand how we go from the microstructural of two particles with a bridge between them to try build up the macroscopic structure of the material, macroscopic response of the material. Again, this is work in progress, so everything here is a little bit more sketchy than what I've just shown. And the general aim is to link small-scale modes of deformation. There are up to 4 modes between 2 particles you can think of. You can apply a force, normal or tangential to the surface, creating compression or shear. You can also apply a moment, which you twist the particles like this, or you bend them like that. So there are four particular responses associated with that. Each of them has a effective modulus that can go with it. And we're going to focus on these 2 modes because those we can explore experimentally. This, we have a numerical modeler on the team, suggests is hard to activate. And this one is very similar to actually what we're doing here. It is fundamentally different, but in that it is a moment being applied to it, but it is very similar. So the first thing we can do actually is, as I said, there is a dependence of the particle size on this. And we also find that the stiffness of the material is about an order of magnitude higher than the stiffness of the polymer, which is an unusual observation. So what we can do is we can take 2 spheres, we can model them with COMSOL, we can put we can fill the gap between them. It's a cylinder truncated by the spherical caps, if you want a specific definition, filled with a polymer. If these are assumed to be rigid, you can then look at the elasticity of the polymer. And depending on the gap size, if you have a gap which is 0.02% of the particle radius, 4% or 10%, you find you get different elastic responses. So if you assume that there's a fixed gap size in there of about 1 or 2 microns, you can then account for the scaling with particle size. Because as you go to smaller particles, the effective ratio of the gap size to the particle size goes down. and you go into a less stiff regime, which agrees with the observations. So it gives us an indication of why there's a particle size dependence, and actually the ratios here say that for particular particle size or particular polymer stiffness, the Young's modulus of this composite object is about 5 to 10 times that of the polymer. So it also agrees with the type of numbers we're getting out of that, where the polymer is noticeably weak, less stiff than the composite material is. Yes. 5 minutes? It's about right. Good. Right. The last part is we can actually do micromechanical testing of this. So we have a glass pipette bent into a weird shape so that if you apply force here, the cap layer will bend with a known moment. So basically it's a cantilever like this. You push, the cantilever deflects, and you can use that to measure a force. And then you can basically have this as a microsensor. You can have two beads which are glued to the PDMS bridge, and you can then apply force and measure the response. Now, does this play automatically? Yeah. So now we're doing that experiment. We can monitor the position of everything to get a stress and strain relationship out of this. And you can get basically the constitutive relationship for a single bead. This is the scatter that was asked earlier. These are individual measurements. This is the radius of the bridge and the radius of the bead. It's basically whatever you can make on this type of scale. You basically get a bridge that size, and then you test it. These are hard to manufacture with any regularity. So you make a few dozen samples, you test them, and you get scatter like this. So even with bridges about the same size, you can see there's a reasonable scatter in the stiffness. Not obvious why, but if you look at this model again, the black and the red curves are basically the stiffness done by COMSOL, where we allow for a 1 micron or 2 micron gap between them. So a lot of the variability can be interpreted as basically there's a small gap between these particles, it's a few microns, and it might be 1 in this pair, it might be 2 in that pair. So that gives us an idea of the constitutive relationship under tension. You can do the same thing for shear. Again, you'll see a short movie of this. It is moving, yeah. Eventually, it should break, or this one doesn't break. Okay. Subtle, but there is a. Oops. You can see a small shear applied to it. So it's basically the same system, pushing like that. Again, you can do observations, and you find it's again consistent with about a 1 to 2 micron gap between the particles. So we have a good idea of what sets the constitutive relationship on the microscale. The next steps are actually to work with, we have a numerical modeler in Israel who's worked on sintered materials before. And so basically the end result of this, which is still a work in progress, we tell him what the constitutive relationships are between individual beads. We tell him the X, Y, Z starting coordinates of the beads, and we ask him to predict the deformation that will occur. And then we truth test that with our Xray tomography observations to basically try to connect those two things from the microscale to the macroscale. In summary, basically, I've started by talking about the kinds of situations where we need a model material to look at fracture properties of things like biogenic or hydraulic fracture, or something where we can look, like Daniel Bonomy's talk yesterday, as a model material for looking at catastrophic failure in general. And I then described how to make such a material where you have cohesive bonds holding together glass beads, and how the material properties of this are highly tunable, where it's basically a moldable material. You can shape it into whatever shape you want. It's chemically inert, a good scaffold for example, hydraulic flow problems as well, where you want to control, for example, elastic response as well as the permeability. Simple, cheap, easy to make. If I have 1 or 2 minutes more, I can show there's a very amusing response here. And this is something, again, extraordinary thanks to Arnaud. And I will end with some fun with balloons. Fun balloons. So take a sponge, squish it. Water comes out. It's a wet sponge, and it's held in a balloon. There's water you can see the water level at the top. So Arnaud's hand will come in and squish the balloon, and the water will go up. Surprise, surprise. You squish a sponge, water comes out. Take sand and compress it, squish it. Water goes into it. This is called Reynolds dilatancy. It's a well-known feature of granular materials. See, sand goes down, or water goes down into the sand. This is something that anyone who walked along the beach, maybe tonight, will be able to explore it. If you step on the beach, you'll see a dry patch surround you as the water gets sort of sucked in. That's basically Reynolds dilatancy, pulling the water into where you're compressing it. If you take our material, and this is largely associated with irreversible deformations. If you take our material, it behaves like a granular material. Watch the water level. If you compress it, the water goes in, but it's a reversible Reynolds dilatancy. We're not actually restructuring the material. We're still putting small strains on, and so it's reversible, so like an anti-sponge. So you can think of it as you have elastic bonds between this. You change it in such a way that you rearrange the particles, but they're still connected to each other. It's a minor change, has the Reynolds dilatancy phenomena, and then it's reversible. You can also test this with the Xray tomography. The porosity increases if you look at before and after stress, after shear failure. So this will be the last chance for questions. I think we have 3 or 4 minutes left.
So, some questions, comments?
Yeah.
Will there be any effect on the plasticity of the beads for polydisperse?
We didn't seriously explore that. We did compare the monodisperse case where we had precision beads of about 1% to the ones we get by default, which are about 15. There was no obvious difference, but it's not something we explored rigorously. Doesn't seem like there would be, it shouldn't be a first order effect, but there should of course be some subtleties in that. Even changing packing fraction, for example. Other questions?
Did you, what's the connection of these things with hydraulic fracture?
So
Did you discuss that at all?
As I said, the idea is to use this as a model material. What's known in hydraulic fracture, the question we want to ask is, it's known that if you add a polymer to the water that you're injecting, it actually makes it easier to fracture porous materials. But there's no obvious reason from fracture mechanics why that should be so. So the idea is we make a large cookie of this material, we put it in a Healy-Shaw cell with an injection point, we push water in under pressure, we add polymer, we do the same thing. We look under the conditions under which fracture happens. So that's the planned series of experiments with hydraulic fracture. And so it's because the kind of materials that would be breaking are reservoirs, which are basically highly porous but rigidly held together material. And the main difference there is that there's a large overburden pressure. So what's normally done is it's looked at under compression, where this provides cohesion without that experimental challenge.
Aren't the polymers that are used typically as propellants or whatever in this type of problems in a fluid or complex fluid state, whereas what you use is a solidified polymer, if I understood well.
So basically we make it, we harden it into place. The polymer that's used for the hydraulic fracture it's just a polymer that dissolves in water. It's a long chain polymer. It changes its viscosity. That's assumed to be its only major effect, is it makes it the injecting fluid more viscous. So the question could be rephrased as that the fracture of these materials seems to have a dependence on the viscosity of the injected material in the injected phase, which we want to test. Does that answer the question? Okay.
As far as I could see from the pictures, these are disordered.
Yes, they're randomly.
Random
We looked
packing,
at that. There is one. If you look at the edges of the cylinder, there's about 2 layers. If you look at the pair correlation function, there's about 2 layers deep that they are correlated.
Yeah.
So there's some wall effects, but the cylinders are large compared to that.
But in principle, you could make crystalline arrangements.
In principle, yes. If you
Will it change anything?
Oh yeah, probably. I mean, certainly. We actually tried strongly to avoid crystalline. So I was very cautious about going to the highly monodispersed materials for working with X-ray tomograms, because I was so worried about crystallization, because it'll introduce directions, it should change things dramatically. I mean, the difference between a glass and a crystalline solid in terms of its elastic response is huge, even in terms of anisotropy right? So
But I'm curious about what kind of changes. Like here you can actually introduce disorder systematically because these are such large particles.
So if you had a lot of patients, you could build them one by one, yes.
That's what maybe shaking or something.
Shaking it is actually challenging, because when you have, even with a wet granulate, there's a large energy barrier to breaking the liquid and reforming it. So shaking a sandcastle requires it behaves as a paste, requires a finite yield stress in order to fluidize the material.
Okay.
So it's not quite as easy as just shaking a normal granulate. You require finite stress before it fluidizes. So could be done. It's not something that we pursued, though.
Yeah, Sean,
So this is regarding the work I am doing on the tension test. So if you take this kind of material, then we see that there is a critical geometry of the system where you go from necking to cavitation.
Necking to?
Cavity formation.
Okay.
So if you see the poster, one of my students' poster outside.
We're not using so you're talking about the fracture test.
Yeah.
Like this. Sometimes you pull, it looks sort of like this kind of test?
Yes.
Okay, yeah.
So can similar things done here?
We could make that kind of test. I had originally wanted to do this with two geometries to confirm, and here I would have made a notch around the edge here, changed the notch size, and looked at the scaling with that. Honestly, it's just a simple issues with the amount of time we had. But yeah, we should be able to make that. We made.
In our case, yeah, we don't start with any notch. If the system chooses
Fine.
the final failure mechanism, in one case
Fine.
you get very thin neck, and sometimes you get cavity, and then it eventually breaks.
Okay. So it should be able to made in that geometry. We've made things close to this, but not this geometry itself. But there's no reason why it shouldn't be able to be made in that geometry. We made stepwise. We made this just for a proof of principle, sort of a bone for a proof of principle test. Not that extreme. This was sort of maybe yeah.
Probably you mentioned this. Can you tune the failure point by the choice of polymer or the kind of polymer?
You mean so we can tune the fracture toughness. The fracture energy we've only changed by changing the contact area. We've not explored other polymers. There will be a different surface interfacial energy associated with different polymers, different surfaces. One thing that probably would affect this is surface roughness. We had some early concerns dealing with different kinds of beads, or basically glass beads ordered from different manufacturers. There were some inconsistencies. So basically, we've always gone with one manufacturer, of beads, because surface roughness will affect things like the interfacial energy. And after some early concerns over that, we specifically went to a single manufacturer. This is actually not uncommon for granular materials, again, because that influences roughness. If you're doing granular physics, this is again advice we got from the granular guy on our team. is just go to one manufacturer. So yes, it should. But we haven't explored that in a way that is rigorous. And it does, because we know different manufacturers of different interfacial types. So.
Yeah, you initially gave an analogy to sandcastle, and afterwards you solidify your materials.
Yes.
So did you study the micromechanics stuff, comparing capillary bridge, a liquid capillary bridge with surface tension and your solid polymer, and what do you expect, or what do you know about the differences that you should have between the two situations?
As I said, the main difference is that this will have a shear resistance to it, whereas in granulates, that shear resistance comes from surface friction. This it comes from which is basically like a viscosity. It depends on it doesn't matter on the displacement. It depends on the displacement rate. So that's the kind of difference here. We're dealing with from my mind, the main difference is that this, if you bend it, will try to come back to its original shape. If you move two grains along each other, they will not tend to try come back to the original. There'll be no restoring force. So that, I think, is the real fundamental difference between the solidified and the fluid contacts.
So if there are no more questions, then let us thank the speaker for an interesting presentation, and let us thank both the speakers of this session. And we will now break for lunch, and then at 2:30 we are coming back. At 2 we are coming back.